Okay, today is the last lab of the day of the year. It's December 7th, Pearl Harbor Day. I'm going to go over lung volumes and talk about some real life scenarios. Starting it up in about 9 minutes. Okay, do you know when the exam is? Monday at 8 a.m. in room 301. Right? Room 301. Down the hall. All right. I'm passing out those minute cards so you can tell me what you would like for us to review, what doesn't need to be reviewed. No, thanks for all your hard work. Before you leave today, that's what you wanted to hear?
So you have to look at one
I'll do it. Okay, maybe you need more time? All right. So the final is comprehensive. That means stuff that we've been talking about all semester is fair game on the final.
That's what I did. Well, that's what I put.
Is there anybody in here who makes a bonfire for Christmas? Anybody in here who makes a bonfire in Gramercy or Luster or Paulina for Christmas? Making one? Every year? You gotta light the way for Papa Noel to find all the little chimneys.
Makes some really good bread.
Mhm. It had sausage in that? Andouille? Right, send them up to the front. I'm ready for those. Alan's gonna put them in alphabetical order. Oh, just what you think is the name.
Oh, you know my name.
Yeah, I don't really need names on those. I'm just kidding. It's anonymous. All right, today I'm going to fill in some gaps. Gaps. Emily, your old papa calls a gap something in your life? You have an old papa in your life that says, "Watch out for that gap." Yeah.
Again?
Yeah. GAP. Watch out for that gap.
You say,
Yeah. With a E.
yes.
Yeah. Yeah, kind of like with a real strong accent, sounds like that. Oh, Walsh? All right. Okay, I'll just handed in a lab report that went over 3 parameters. And part of the take home of that was not just to think of these as separate, but that they all really work together. Right? When the body is under stress from exercise, or if you're running away from some kind of Bigfoot creature, cardiac output goes up in order to deliver oxygen to your muscles. Total peripheral resistance goes down. Why does the total peripheral resistance go down, Ms. Frangella? Yeah, vasodilation. Leads to TPR going down. And that stabilizes the mean arterial pressure. So we could describe that as what's going on with the cardiovascular system. But at the same time as the blood being pumped faster and quicker with bigger vessels and our blood pressure being stabilized through homeostatic mechanisms, there's really sort of like another side to that. And that's what's going on with respiration. So I wanted to fill in the gaps on that story a little bit. At the same time that your heart is pumping faster, you're also ventilating faster, right? And it's pretty similar to what the heart's doing. What's the heart doing? Cardiac output. Heart rate times stroke volume. There's 2 things going on here with the cardiac output. The heart rate increases in frequency. Stroke volume is the amount of blood that's going through your heart, right? The amount of volume. So in the same way, our lungs are doing that too at the same time. They're connected by our bronchi to our trachea. And we're moving more air and we're taking more frequent breaths, right? So what's kind of similar to heart rate, we're talking about respiration. Kind of similar to heart rate is respiratory rate. What's kind of similar to stroke volume is what's called tidal volume. Okay, so at the same time that your heart is pumping faster, you're also breathing faster. I know that makes it's actually so simple that it almost seems like it doesn't need to be written on the board, but I'd like for you to make sure that you know that at the same time that the heart is increasing its activity, the lungs are increasing their activity. And like I said before, you know, when you take in a big deep breath, when I do, it feels like I'm controlling all that right here. But Tyler, where am I really controlling that? Okay, your brain is doing some of that. Jerry Lynn, am I sucking the air in with my mouth? Is my mouth making the air come in? What is? It's really this muscle way down here, this diaphragm. See what I'm getting at? It feels like it's here, but it's really here. It's a weird thing, right? I'm not making fun of it, but I want to make sure if you talk about this, it's really like the lungs, they're not quite doing the work that the heart is, right? The heart's really the muscle. The lungs are where respiration is happening, where blood comes into close contact with air. Blood does not touch air, but it comes into close contact. But getting the air into the lungs is accomplished by this diaphragm. Brings it in. Right. There's this little toy. Aaron, you played with this before? See, like this is like a diaphragm, right? I'm gonna pull it down, watch. Oh,
So what happened before I broke it? It inflates the lungs, right? Okay. So this is kind of real and kind of not real. What's real about it is our diaphragm really does take in air that way. But our lungs are not really like little balloons, right? They don't really show up like that. They're pretty cool. It's pretty cool. Okay. So the lungs plus our diaphragm is leading to a higher volume of air that's moving in and out, and a respiratory rate, like we're breathing quicker. So when you start running a mile, you notice, oh yeah, I'm breathing deeper, I'm taking it in faster, pushing it out faster, and it's more air coming through. So instead of cardiac output, our word for that is the respiratory minute volume. Cardiac output is in liters per minute. The respiratory minute volume is in liters per minute. Yeah. So those work together. Did I see your hand go up? Or somebody was just stretching. Hey, Danielle, have you heard of that measurement that I just said, tidal volume? We talked about tidal ventilation, right? So what's something that is alternative to tidal ventilation, like another kind of ventilation?
We talked about ram ventilation.
Yeah, like ram ventilation in a shark, that just means water is always going through. But in tidal ventilation, air goes in and air goes out the same hole. So there's a slight inefficiency there because new air mixes with old air. Yeah, the residual volume. Right. So I would like for y'all to be familiar with this group of lung volumes. And this is a kind of a famous graph that you can find in just about every textbook. And in human males, the total lung capacity is sitting at about 6.0 liters. That's the total lung capacity. All right. So this is one way to think about how much air we can move in and out of our lungs. When you're sitting at rest like y'all are, you breathe in and you breathe out, in and out, and it's not much. You're not taking a deep breath right now, right? You're taking a small breath because you're not exercising. You don't need a big breath. This small amount of air right here is about 500 mils. We're going to call that 0.5 liters. Right? And that's called tidal volume. Julie, you heard of that before? Miss Southall, you heard of that?
Yes.
All right. So I told you that that's a little breath. Julie, you know what you call it when you suck in a big breath? All right. So this is a little breath that I just took right here, like y'all are all doing. But then you could take a big breath in. That big breath there that goes in like this, that's called your inspiratory reserve volume. Inspiratory reserve volume. In conversation, we tend to say inhale, but in physiology, we say inspirate or inspire, right? Inspiration. It's not the same as like a dream. This inspiration is similar to an inhalation. Okay. Normal breathing in and out. And when you normally breathe in and out, you're just breathing out a little bit like y'all are doing right now. But if you were trying to blow up a air mattress you would blow even more out, right? That amount is like in opposition to the inspiratory reserve. That's the expiratory reserve. Expiratory reserve volume. An expiration, in this case, is like an exhalation. In conversation, we usually say you exhale. In physiology, we say you are expirating. It's an expiration. Right? So I said this was 500 mils. This amount that we can take in right here, that's about 3,300 mils. We're going to call it 3.3 liters. This amount that we can push out is 1 liter. So as it turns out, these three amounts, I'm going to put them right here. The tidal volume plus the inspiratory reserve volume plus the expiratory reserve volume, they equal this big amount that we can control with our own diaphragm voluntarily. We can breathe in a whole lot, we can breathe out a whole lot, but in a normal situation, we're just breathing our tidal volume in and out, in and out. That's called our vital capacity. Vital capacity. And that goes from this amount, breathe out, all the way to this amount that we suck in. This is our vital capacity. So if you add these all up together, 3.3 and 1 and 0.5, in males, it's about 4.8 liters. Now, Mason, why do you think I didn't bring it all the way to the bottom here? Is there another volume that I talk about when I talk about the lungs? That mixing volume? What do you call that? Residual volume. Now you can sort of tell, maybe you can't tell. You can't get rid of your residual volume, right? The only way to get rid of the residual volume is like if you have a cadaver, open up the cadaver and you smush the lungs, totally smush them like a balloon. Okay, then you can push out what that is. That's about 1.2 liters. That's what I mean by there's always a little bit of old air in our lungs. That's what 1.2 liters sitting in there. That's the male amount. New air comes in and it mixes with this old air. But it doesn't really matter because there's so much oxygen in air. There's plenty of oxygen for us. But if you take all those together, what's that called, Miss Erin? Residual volume plus the vital capacity. TLC, total lung capacity. Total lung capacity, which for males is about 6 liters. And for females, it's about 4.8 liters. It's about 20% less. Just because on average, females are a little smaller. Okay, y'all seen that before? That's usually taught in most anatomy and physiology classes. We didn't mention it here, but all of that goes into what's going on during exercise. Right? During exercise, our heart's working more. During exercise, our diaphragm is utilizing our lung differently. So I didn't necessarily get to that final part of the story, but this is at rest. At rest, this is your tidal volume. It's about 0.5 liters. What happens when you start to run around the block? Reason that we call this the inspiratory reserve is now your tidal volume can go up into that reserve. And what you're pushing out can go into this expiratory reserve. Right? So you see what's happening here. At exercise, my tidal volume is increasing. Because I've gone into my inspiratory reserve and into my expiratory reserve. Does that make sense? At rest, respiratory minute volume might be, let's say this is respiratory rate times tidal volume. This might be 0.5 liters at rest. 0.5, just 0.5 liters per breath. But at exercise, it jumps up, might go up to 0.1 liters. Just like the stroke volume increases, the tidal volume increases. Right? Respiratory rate at rest might be sitting something like about 8 breaths per minute. When you start running around the block, it goes from 8 to 16 breaths per minute. Okay, so if you multiply this respiratory rate times this tidal volume, now you're breathing a lot more air in and out of your lungs. So that goes along with cardiac output. So not only are you moving oxygen, but you're also harvesting more oxygen by modifying your tidal volume. Mr. Dubersan, does that make sense? Have you heard that story before? Yeah. So the key is your tidal volume increases. And the way it can increase is that you're going into this portion that you never use. And part of what I want you to understand is that the lungs do not really change their size. Right? That would be something that someone who didn't understand this might think your lungs are getting bigger. Your lungs are not getting bigger, so your lungs are staying the same size. But you're able to push more air in there because you're using this portion of it, the inspiratory reserve and the expiratory reserve, that you don't usually have to use. Right? In the same way that we were able to measure blood pressure without electricity, I'd like for you to see how to measure these lung volumes without electricity. So if you go to a hospital or respiratory therapist, they got some pretty fancy stuff over there. But it really does not take much to measure these lung volumes. You can do it without electricity. And what you do it with is this instrument here, which is called a spirometer. It's called a wet spirometer because we're using water. The water is displaced by my breath. You can measure how much each one of these amounts is. So even though I am lecturing, I'm not exactly at rest, but we're going to kind of say it's like I'm at rest. And we're going to measure my tidal volume, my inspiratory reserve, and my expiratory reserve volume. By getting these three, then we can also calculate my vital capacity. It's just the sum of those. Ms. Kelsey, you ever did this? All right. So it's our last day to be face to face. I'm going to take off my mask for a minute. Ready? This is my mouthpiece that I put on here yesterday. Right. If this goes up to 1 right there, if you got 1, Alan, that means 1 liter. Right now, I'm zeroing it out at 0. Jerry Lynn, can you see it's at 0 more or less? This fancy little pin here. Right. We're just going to take normal restful breaths. And you're going to see what my tidal volume is. Just resting, I'm breathing. Again, an inspiration. And so it's about 0.8 liters, not really 1 liter, 0.8 liters. Same as 800 mils. Sometimes you gotta do it twice, once or twice to get a good one. I might have been stressed out, and pushed too hard. It's hard to breathe normal and breathe on strong. That's 0.8 or 0.9. 0.80 liters. That's my tidal volume. Now I'm gonna breathe out normal. Breathe out normal. That's my tidal volume. And then I'm gonna breathe out like I'm trying to push air into an air mattress. I'm gonna push everything out that I got. So I'm breathing out normal. Right? So that extra amount that I breathed out was about 1.8 liters. That was my expiratory reserve right there. 1.8 liters. Is anybody confused yet? I just got my tidal volume and my expiratory reserve. Now, it would make sense. How would you get your inspiratory reserve? You suck, right? But you don't do that on these wet spirometers because it would suck in some water. Now, water is not dirty because I got it from the tap, but still might be kind of dirty. Renee, you did this before?
I actually did it in Dr. Sal's lab for 117 with machines similar to that.
You know how we're going to do it now?
I don't remember now.
Okay, what I can get, if I can't get the inspiratory reserve, you know, your math, see what I can get is this. The vital capacity. You know how I'm gonna do that? I'm gonna suck all the way in and then push it all the way out. You see how that's my vital capacity? I've sucked as much as I can in, and then I blow as much as I can out. And what I've gone through all these. Does that make sense to you? All right, so I'm gonna do that now. Are you worried? Yeah. Alan, are you worried? You look worried. All right. That's you. So I got about 4.3. My vital capacity. Vital capacity equals 4.3 liters. I'm gonna add these together. 8, 9, 16, that's 2.6. If I take 4.3 and subtract 2.6, I can get my inspiratory reserve volume. 13.67. So now I have all three. 1.7 is my IRV. My tidal volume was 0.8. And my expiratory reserve was 2.6. No, 1.8. 1.8. So if I add all these together, they come up to this big number, 4.3. That equals my vital capacity. Just so you're right, does that make sense? Vital capacity. Now we can estimate what my residual volume would be, which would be like 1.2. So my TLC, my my total lung capacity would be about 5.5. Right?
Average is 6.0. Mine today is 5.5 liters. That's my total on the test. Y'all see how I did that? Without using electricity? Saw how I used a spirometer. Now, it's easy to get that mixed up and think what that thing is a respirometer. You see? But it's not a respirometer. It's just a spirometer. Kind of the same root spirometer. Wet spirometer. How do you measure blood pressure? A sphygmomanometer. How do you measure lung volumes? A wet spirometer. Right? That gives you something to think about. That might be on the next exam. While we're talking about exercise, I wanted to cover something else. I wanted to re-emphasize something about what goes on during exercise. One way that I think about it is that our homeostatic mechanisms have been evolved for exercise. Evolution worked through what? Through natural selection. To optimize homeostasis during exercise. What I mean is, like, exercise is kind of a normal thing that our body is made for. You got to run away from a bear, or you might be running to try to catch a rabbit, right? Our body and the body of the other apes that we evolved with are made to run every now and then. And so that's why our body works well during exercise, for the cardiac output to go up, the total peripheral resistance to go down, the mean arterial pressure remains stabilized, and the respiratory minute volume goes up. Because our body knows how to do that. But, Mr. Jones, can you think of a situation that our body does not know how to handle as far as respiration and cardiovascular physiology? That's tricky. I'm gonna tell you. But it's something that I mentioned before. It's like our body did not evolve to be in a hot air balloon. Right? What happens when a human goes up in a hot air balloon? Quickly goes up to altitude. Can I remember this story, Miss Emily? What happens? What happens to our homeostatic mechanism? Abby, how would you explain what happens to our homeostatic mechanisms if you're stuck with the Wizard of Oz in a hot air balloon? You wave into the crowd and they get smaller and smaller as you go up. You know what I'm saying? You know what happens? Okay, Julia, you know what happens? Tyler, you got an idea?
As you go higher, just less pressure, and like you go higher in altitude.
All right. Like Danielle is saying, during regular exercise, your oxygen goes down. During regular old exercise, your CO2 goes up. Right?
When these things happen, your pre-Botzinger complex tells your diaphragm, you gotta start breathing more and your heart starts pumping more. This is normal. During exercise, our body recognizes this stress correctly. Brianne, did you get what Danielle was saying?
Yes, sir.
Can you repeat what she said about the hot air balloon?
The oxygen and the oxygen and the CO2.
See what's different about when you go to altitude, there's also no CO2 up there.
Right, because the air is thinner.
It's not like normal exercise. You start running out of oxygen, but your body doesn't realize it because the CO2 is low. Taylor Martin, you get that? You know what I'm talking about there?
Yes, sir.
It's because your pre-Botzinger complex, it turns on the alarm when the CO2 is high. But here you are at low CO2. In a normal exercise situation, boom, 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 the alarm goes off, you start breathing more, right? That's what happens when you run. When you go up in a hot air balloon, you need more oxygen, but nothing. The pre-Botzinger complex is not telling your diaphragm. It's not telling anything. And so you're breathing normally, but you're starving of oxygen. You just breathe normal. So what happens, Courtney?
You basically suffocate.
Yeah. You get kind of sleepy. So I'm just going to lay down for a minute and you die. You suffocate almost painlessly. Your body doesn't even know to gasp for air. Right. So in a way, this seems like a pretty goofy thing to memorize, but for me, it's a good example of how homeostasis works correctly in exercise versus a situation that we were not evolved to do. It's like for millions of years, apes have not been going up in hot air balloons. That's why we can't do that. But geese can. Geese can do that. Geese and pintail, they go way the heck up there, and they can fly for 500, 1,000 miles a minute. They can do that. But we haven't evolved for that. On the other hand, you could look around the globe, maybe, for a few pockets of people who don't do this, but they live up in the mountains. Like Mackenzie Martin, can you think of an example of what I'm talking about? Not a hot air balloon, but up in a mountain. There's these little populations. Mr. LaBeouf, you know what I'm talking about? Mr. Claymore?
I think they have like a group of people that live in Nepal.
Nepal. That's the
India,
Himalayas.
Yeah, and they have really good O2 concentration.
Himalayas and the Andes in South America, where the emperor got his groove made. Himalayas, Andes, maybe even Native Americans in the Rockies, in the Alps of Europe. There's always been a few populations that live up at altitude. So this is the way they compensate, right? So you're getting to it. They're able to hold more oxygen somehow. And here's some of the examples. They tend to be small stature and barrel chested. So their whole thoracic cavity is bigger. It allows them to take in more air. That's first. Number two, they have more erythropoietin that leads to actually more red blood cells. So you take a hematocrit of me, that's my red blood cell count, versus a hematocrit of a native person from Nepal, like Michael said, and he has a lot more red blood cells. They can't really pack more hemoglobin into the red blood cell, but they got more red blood cells. So that's the way they compensate and are able to live at a place where there's less air and less oxygen, but still harvest the oxygen that they need. Right? Does that sort of make sense? Those are extreme situations, but those extreme situations kind of help us understand what's really working in our system on a daily basis when we're not in an extreme situation. Right, right. Okay, now I'd like to think about a nice story for us to end our semester on. Okay. The name of this story is Anniversary Surprise. This is a fictional account that has some local components. So let's just say there's this couple named Grant and Becky, and they're going out for their anniversary. They want to go look at the bonfires. The night that they burn the bonfires, that's Christmas Eve, that's a good night to go see them, but it's also very crowded and there's a lot of people drinking. You go the night before or the night before that, and you can see all the bonfires and kind of check them out. So they kind of know about that idea. So they don't go on Christmas Eve, they go on Christmas Eve. Christmas Eve. And they're gonna go do the run from Gramercy to Paulina. That's where you see all those bonfires. And they're gonna go all the way down to Garyville. Robert, you know who they're gonna check in with over there? It's this group of outlaws called Blood, Sweat, and Bonfires that make a sculpture every year, an artistic bonfire sculpture that sometimes it even moves. Like one year it was a big alligator snapping turtle, and you could pull on this handle and the mouth would move like this. One year it was a pelican with some babies, and you turn this crank and the little babies would nip up at the mom. So they're gonna go over there and they're gonna go hang out with some of the people making the bonfires. And this is the first situation that I want you to think about. Because everybody's like tailgating over there. Somebody says, Grant and Becky, I'm glad y'all celebrating y'all's anniversary. I want you to have some of these squirrel brains. There's a delicacy that my family makes every year. They say, okay, we're gonna try that. Then they say, we gotta go. We're going to our next spot. So they cross the bridge and get back on the west bank, and they start to go through Boutte. And as they're over there at Boutte, they see the Davis Pond diversion. And because Becky has never really looked at the Davis Pond diversion, they stop and feed some gators. And Grant tells her all about the problem, the causes, and the therapy that might fix the Louisiana coast. But they're not stopping in Boutte. Of course, you know where they're going. They're going to Moskos for their special night, their anniversary. At Moskos, they got a reservation, and they order oyster Moskos. You had that before? Is it good?
That's really
In oysters Moskos, there is some protein that comes from the oysters. There's a bunch of butter. which equals triglyceride. And they bring you some little crackers, which is a carbohydrate. Oh, they're celebrating. So it's their anniversary, so they also get some champagne, which wreaks havoc on their renin-angiotensin system. 1, 2, 3, 4. Now, all of this seems like a pretty good surprise, but that's not really the anniversary surprise. The anniversary surprise is, it just so happens that they have a surprise encounter with the stork. It wasn't exactly on their schedule, but Becky's ovulating. So I would like y'all to think about the ovary, the hypothalamus and the pituitary, and the endometrium that would lead to a successful fertilization. How we could plot that out. And the biggest surprise is about 6 weeks later, that little zygote that gets started on that night becomes a beautiful little female. And so how does that happen? That's story 5 and 6. Okay, Mackie Martin, is one of these attract you? If you would tell this story? Okay, you're gonna tell this story? So you're gonna use that poster and those markers in front of you? And you're gonna remind us how sex is determined in a mammal and a human. Starts with the chromosome, goes through the endocrine system, and you have some changes in morphology, right, to make it female. So before y'all start working on that, I'm warning you, you don't want to put it like this, because the sticky is just on the top, right? So you can't do it in landscape, or when you put it on the wall, it does like that. That's no good. So there's a top to all of these. All right. Miss Hugh, is there one that's attractive to you? Okay, Mackenzie, your group is at 4 right there, huh?
We want champagne.
All right, all right. Okay, you got 4 people to help? All right. Ms. Southall? Okay, you go on to Moscas? All right, you got 4 people right there. Mr. Barrett, you gonna be on that group? All right. Mr. Batto, one of these seem attractive to you? I got a, huh? Number 2. That's the Davis Pond diversion. So you're going to draw Louisiana, right? That's Matthew Batto and his group. That goes to Brandon and Mr. LaBeouf. All right. You all ready? What's the left? Fertilization. Anniversary surprise. Can y'all handle that? Okay, you know what that's going to look like? Most of that, it could be a graph with the endometrium and with the ovary, with the hypothalamus, and ovulation night is right here at 14. Or you could draw the uterus if you wanted to. Okay, so what's allowed? You can take out your textbook, or you can Google it, or use Wikipedia. Doesn't matter to me if you want to use some of the notes from this class. Huh? You got squirrel brains. All right. Mr. Barzone, you got squirrel brains. You think you know what happens there? This is what I want y'all to describe. Yeah. Oh, let's see how these are curves.
Yeah, similar to like Matt.
Yeah, and we're back out. So. I'll make a story. You can act like it's a deer and tell the same story. The squirrel brain has some kind of feeling in the brain that goes through their stomach. Retrograde goes up into their brain, and then these bad prions change the good prions proteins, and they can capture energy. And then that person, that human, starts to get holes in their brain, which is called Creutzfeldt-Jakob. Yes, sir. From there, it's one of those, in a bird, but did he have a girl disease before he died? Was he still alive? I've never heard of it. No, I guess that's why. Okay, you understand? Yes, you have to eat squirrel brains, that's the story. You don't have to really eat squirrel brains, that's the story. But if Robert wants to act after for like several years, you write down the words you have to write down.
I want a Coke.
And what's wrong?